Swayam Prabha. Digital India. Educated India.
Welcome to this course on transition metal organometallics in catalysis and biology. In this regard, we have been discussing olefin oligomerization reactions in the past few lectures, and today we are going to finish up the discussion on olefin oligomerization or alkene oligomerization, and if time permits we start with the topic alkene olefin polymerization as well. So, with that let me just give a brief overview of what we have been discussing in the previous lectures. As mentioned earlier, that we had started off with ethylene oligomerization in the context of SHOP process, cell higher olefin process, and then we have looked into ethylene trimerization using a tantalum catalyst. This was a work by Professor Ayushman Sen, where one could produce one hexene selectively by trimerizing ethylene. The third that we had spoken about in this under this topic is this propylene dimerization in terms of producing various kinds of branched hexanes. This also is a industrially applicable reaction which is used for application in auto industry, particularly these branched hexanes when hydrogenated are very good anti-knocking agents and are used in petrol for their attributes. So, after trimerization of propane, dimerization of propane producing branched hexanes, we then looked at trimerization of butadiene, which gives this cyclododeca triene, which is a cyclic compound ring with three unsaturated olefinic bonds, and each in a trans configuration. And subsequent that we have also looked at the Ziegler-Natta way of preparing this cyclododeca triene using Ziegler-Natta catalyst, titanium catalyst. And today we are going to discuss butadiene dimerization. So, the one that we had spoken about earlier was butadiene trimerization, and today we are going to talk about butadiene dimerization. Cyclodimerization of butadiene. Now, in order to take up this topic, we should refer to the earlier discussion of cyclotrimerization of butadiene. And this was reported by Wilke in 1960. Now, the difference between these two processes is that the earlier one was cyclotrimerization process, where dodeca triene was obtained, and this today what we are going to be discussing is a dimerization process, where we are going to make octadiene, cyclic octadiene. So, there is the difference in the product which would be formed because of dimerization and obvious trimerization process. However, there is lot of similarity in the process as well. For example, both involves a substrate butadiene. So, the today's one is a dimerization of butadiene, and the earlier on we had discussed trimerization of butadiene. And furthermore, the other similarity is that the catalyst precursor is same for both. The catalyst precursor is same for the both, the one which is dimerization and the one for the trimerization as well. And let me just draw the catalyst precursor. So, this bis allyl nickel complex is the catalyst for cyclodimerization process, and also the same is true for the nickel butadiene cyclotrimerization butadiene process. Now, the difference lies in the final product. One is for the dimerization, the other is the trimerization, whereas the similarity is that both are of butadiene and both require the same catalyst. The only other difference is that this butadiene dimerization proceeds in presence of phosphines. And they results in dimerization. So, when phosphine is present with nickel allyl catalyst and with butadiene as a substrate, then primarily the dimerization product of the butadiene is observed, whereas when nickel allyl with butadiene is present exclusively, then the trimerized trimerized product observed. So, in this case, when phosphines are present, then the product distribution, the dimerized product distribution can be controlled by varying R or the alkyl group of the phosphine. So, that gives a useful handle on how this dimerization process occurs. So, now let me just give the scope of this reaction in terms of the different products being formed. And this is shown over here. This reacting with 2 butadiene in presence of phosphine, we had observed similar reductive elimination. So, this over here nickel is in +2 oxidation state and reductive elimination of these two species occurs to give the diallyl compound as is shown over here, and this is quite similar to what had been observed for during the cyclotrimerization of butadiene process, where 2 diallyl compound was evolved, but please note that this triaryl phosphine was not present during that time, and resulting in this product. bis allyl nickel product bis allyl nickel product again the oxygen state oxygen state of this has +2, but like last time this reaction sort of can proceed as is shown over here. This would go via the formation of bis this nickel 0, and that in presence of PR 3 would give this nickel 2 compound that would involve this oxidative addition of these two to form this ligand, and then nickel becoming nickel 2. So, this process sort of is a two step process where a nickel 0 is formed, followed by that. Now, these once this is formed, then that can reductively eliminate to give chord cyclooctadiene polymer, or these can be in equilibrium to give this compound. So, here the allyl moiety has just become a sigma donor, and the other allyl moiety also has become a sigma donor as it is shown here. Now, this can again undergo reductive elimination to give this 6 membered compound cyclohexane compound as is shown over here. Similarly, this the central species can also become this nickel metallocycle as is shown over here, and that undergo reductive elimination to give an interesting compound cyclobutadiene compound of this type. So, what is seen over here that this dimerization of butadiene, dimerization of butadiene as is shown over here can occur to give the cyclooctadiene in presence of phosphine. However, in presence of the different substituents of phosphine, there can be other products which can be also obtained from the reaction. For example, if there is this particular kind of 2 sigma allyl reagents are formed, sigma bonds to nickel are formed, then one 6 membered ring can be obtained, whereas if this nickel cycle 5 membered ring is formed, then cyclobutane with 2 vinyl substituents are obtained. So, this is a nice demonstration again of the ability or scope of organometallic catalysis, where a variety of substrates can be obtained depending on the sterics that one uses. So, with this we come to this end of our discussion on cyclodimerization of butene, and also we conclude our discussion on alkene oligomerization reactions. So, to summarize, we have looked into variety of alkene oligomerization reactions, starting with ethylene oligomerization for in the context of shop catalysis. Second one is ethylene trimerization to obtain 1 hexene. Third one that we have looked at is propene dimerization. Fourth one we had looked at is trimerization of butadiene, and fifth one again we have looked at in this context is cyclodimerization of butadiene. So, we have looked at 2 reactions of butadiene, dimerization and trimerization. We have looked at 1 reaction of propene dimerization, and we have looked at 2 reactions of ethylene trimerization and oligomerization. It is important to mention that in all of these cases the catalyst which are used is nickel, except for in ethylene trimerization, where tantalum was used for catalysis. So, this further reinstates nickel plays as a metal of choice for producing oligomers of different degrees, cyclic and acyclic from olefins, and that reason being that more electron rich late transition metal are good for alkene oligomerization, whereas early transition metal are good for electron deficient early transition metal are good for olefin polymerization. So, with this we move on to another interesting topic, which is olefin polymerization. So, now we are moving on from low molecular weight oligomers of olefins to high molecular weight polymers of olefins. Now, olefin polymerization is an important reaction in terms of producing polyolefins, and it is sort of synonymous with Ziegler-Natta catalysis. However, there is more to olefin polymerization than just Ziegler-Natta catalysis, and different types of polymerizations that are possible for olefin, and Ziegler-Natta though constitute a primary portion of it. So, this is a application which has seen the light of the day in terms of the application moving on from the discovery in the within the confines of laboratory to being practiced large scale in industry. So, polyolefins are produced industrially for making macromolecules. polyolefins are structurally produced for making macromolecular materials. Now, the importance of these polyolefins can be gauged by the extent of production that is required to meet the daily our daily need or the need for these plastics. So, the increased production of polyolefins over 70 megaton annually is mainly due to wide spread applications of polyolefins. So, this is mainly due to large scale applications of polyolefins. Polyolefins are applied for various purposes, and the demand for polyolefin is met by increasing the production, and really a large amount, about 70 megaton of polyolefins are being produced annually to meet the demand. So, because of its large scale application, the knowledge about structure property relationship and the development of new catalyst for polymerization is important. The knowledge of structure property relationship is important for catalyst development. Now, this is a important attribute, because this is where the mechanism the insights about the mechanism come into play, because if one were to know the mechanism fully well, then one can come up with modifications which will enhance the catalytic attribute of this catalyst performance for this process, and produce improved polymers. So, there is the research primarily in this direction are focused in understanding the structure property relationship or structure activity relationship as a function of catalyst structure. And another thing about polyolefin is that not only its polymers are important, but also the segmental mobility or degree of branching is important with regard to determining what kind of polymer material it would be, whether it would be a hard brittle kind of polymer, or would it be a soft ductile kind of polymer. So, the important term over here is segmental mobility depends, mobility is an important property that depends on the degree of branching of polymer. So, what we see that polyolefin is an important area overall. This is what the take home message from here, in the sense that this has gone big and went on to be become as one of the biggest industrial process for making large macromolecules. And then the demand for polyolefins or polyolefinic materials are so high that annually of about 7 T megaton, that is a huge amount of polymers being produced. Now, this widespread application of polymers in different different applications, for example, from furnitures to bottles to other to devices, to utensils, to everything. That depends on the nature of the polymers, and to understand that the mechanism of the polymerization is very important, and for obtaining insights on the mechanism, the structure property relationship as a function of the catalyst structure is important for developing better catalyst, which will produce more controlled and better polymers. And lastly, the segmental mobility of the polymer is an important property that is dependent on the extent of the branching of the polymer, and then the need comes to make polymers which are branched, and then exclusively make polymers which are non branched or linear, and their overall property would depend on the extent of branching or the linearity. For example, if a polymer is branched, highly branched, then it will be more soft material, whereas if the polymer is long chain linear polymer, then it will be very brittle and hard. So, depending on the application, there is a need for producing each of these types of different polymers. So, with this I come to an end of today's discussion on olefin oligomerization as well as olefin polymerization reactions. To begin with, we had finished our discussion on the topic of olefin oligomerization by discussing cyclodimerization of olefin using a nickel allyl catalyst. This is very similar, the catalyst is very similar to that of the reaction cyclotrimerization of olefin. The only difference is that in the cyclodimerization of olefin, phosphines are used, and depending on the types of phosphine used or the steric bulk of the phosphine, one can not only produce the cyclooctadiene, which is the cyclodimerized part of butadiene, but also can one can obtain 4-membered cyclobutane or 6-membered cyclohexane rings, depending on the nature of the R group of the phosphine. We have looked into that, and then we have looked into this important process of olefin polymerization. We have looked into the need for large scale production of this process and how they are being met by organometallic catalyst. We have also noted the importance of the knowledge of structure property relationship in respect to catalyst development, and lastly, with respect to the polymer properties, we have discussed about the importance of branching or segmental mobility of the polymer, which sort of defines the very nature of the polymer. So, with this I come to an end of today's discussion. We are going to be talking more on olefin polymerization, particularly about various types of polymer and their attributes when we mix next, and then look into how what are the various examples and the types of polymers that are there. for this under this topic of olefin polymerization. So, with this I once again like to thank you for being with me in this class, and I look forward to be discussing this olefin polymerization in great more detail when we meet next. Till then, goodbye and thank you.